All right, so I've got the 4 p.m. session, so I need to encourage a bit of audience participation for this next part. So I'm going to be talking about copper today. Hands up who thinks they might have copper on them right now. Keith, I reckon you've probably got some as well. So obviously the smartphone is one aspect where we find copper on ourselves when we're walking around a conference. But you might even have it in your clothing as well due to its antimicrobial properties, or even in your blood. But in any case, I'm going to talk a bit about copper today. My name's Dave. I'm a metallurgist by background. I started my career in operations, and these days I lead the technology management team at Metso. So I'm going to talk about copper, why it's so important. We're going to take a bit of a look at mining and refining of copper, and I'm going to define the difference between those two. And then we're going to look at supply projections of mines and the refineries and the demand, and this takes us to our challenge. We'll then look at a bit of a history of copper production and challenges that the copper industry's faced over the last 300 years and what innovations have resulted from that. And we'll conclude on perhaps a bit of a look towards the future. So copper, why is it so great? Copper is great because of its unique combination of characteristics. It's excellent for conducting electricity, and at this point in time, this is the primary use of copper. There isn't a great substitute for copper. There are some, but the applications are quite limited. You could use plastic in piping, for example, or you could use aluminium in some quite specific applications in electronics. The challenge with aluminium is that it produces a lot more carbon, about 5 times the carbon emissions, and it conducts more heat, so it's not really suitable for electronics. Why copper is so important to the energy transition is because of the way in which we use electronics is changing. And an example of that would be, for example, a car like a Tesla Model Y has about 83 kilos of copper, as opposed to an equivalent ICE vehicle that has about 21 kilos of copper in it. The transition towards clean energy, things like wind turbines, have an awful lot of copper, about 29 tonnes of copper in a wind turbine. And then if that's located in the middle of the ocean, you need to bring that electricity to the coast using a significant amount of copper. The way we use electronics in our homes is changing as well as we move away from perhaps gas heating towards the use of electricity. That means we need to upgrade grids to support and supply electricity to our homes as well. So mining versus refining of copper. Mining is when we talk about mining copper, we're typically these days mining somewhere between 0.1 to 1% copper of a feed grade, and then we concentrate that in using a process typically like flotation to about 24% copper grade. That then needs to be refined, and you do that using a combination of pyrometallurgical techniques like smelting and hydrometallurgical techniques like electro-refining. So when we talk about mining of copper and we look at the countries that dominate that, it's very much the South Americans. And when we look at the refining of copper and the downstream processing of that concentrate, it's very much China that dominate that area. If we take a look into the future, particularly around 2035, these graphs illustrate a pretty substantial difference between what the mines are able to produce, including new potential projects, and what the refineries are able to produce. Even at this point in time, we've got a gap, so there's a short supply of copper concentrate to feed the refining operations, but by 2035 it's about 30% that the forecasters are projecting. So I guess the question is this just bad forecasting? Will we be able to find more projects during that time to improve the outlook? And is there anything else we can do with existing and new copper mines that might be able to fill some of that gap? This is the conundrum in essence. So what's in a copper project? When you've got a greenfields or a prospective greenfields operation, first of all you need to find a deposit, you need to drill it, develop it, conduct a feasibility study, evaluate the economic viability of it, get permits, approvals, funding, and then finally you go on to construct a mine. So typically that process takes about 17.9 years on average, and that time frame has been increasing. So in the modern day, this is what a flow sheet would look like when you construct a greenfield sulfide concentrator. You take raw material, you put it through comminution, you float off a concentrate that you can then upgrade using smelting and electro-refining. Metso, the company that I work for, have technology across the entire flow sheet, and we've had a long history in developing innovative products for the mining industry and in particular copper. So so our company has been around for a number of years, about 150, but we're going to take a look back over time of over 300 years and have a bit of a look at the whole of copper production. So the challenge, as I mentioned, we've got increasing capital intensity for greenfields and brownfields on top of the fact that we don't have a lot of projects. The operating costs like energy, labour, shipping, ESG requirements and geopolitical aspects aren't helping this. And compounding the issue is the fact that ore quality has been declining globally for some time. So since 1991, the average copper feed grade for a plant has dropped about 40%. In the last decade or so, exploration activities around copper have very much been focused around expanding brownfields and extending the life of a brownfields operation, rather than the generative exploration that yields new greenfields deposits. I mentioned it takes 17.9 years for that process for developing a greenfields process. So this means that a greenfields operation. So this means that it's not a quick ship to turn around when you want to go find new greenfields operations. The recent levels of approvals since 23, 24, for example, have been pretty limited, and compounding that is getting a greenfields project approved is not straightforward with rigorous ESG requirements around them. So some of these challenges that I've talked about are new, some of them aren't. So now we're going to take a look at history and see what we can learn from history. Okay, so where do we begin? We begin in Swansea in Wales in the 1700s. So this was the birthplace of reverberatory smelting of copper ore. So back then, you would take the whole of the copper ore and put it in a furnace and smelt it. So this used an awful lot of coal, about 3 times as much coal as it did copper. So it made more sense to do the smelting where the coal was in Swansea rather than where the ore was in Cornwall in the UK. So this pictured copper works opened in 1717, and for the next 150 or so years, this method of producing copper dominated, and Swansea became responsible for about 65% of global copper production. So that ended the nickname Copperopolis. Chile and Australia were also notable mentions in copper production, with South Australia being nicknamed the Copper Kingdom back then. But direct smelting in reverberatory furnaces had its problems. Recoveries were poor, it used an awful lot of fuel, smelting required many steps, and it was a very dirty and a toxic process. This wasn't helped by the fact that any ore sorting that they did do was done using child labour. By the end of the 18th century, the world was starting to run out of high-grade ore. So when we talked about high-grade ore back then, it was about 4%, which is, for context, about 4 to 20 times what we would put through a plant these days. And the energy cost of that coal was going up as well. So this was making direct smelting of ore increasingly prohibitive. At the same time, the world's population was starting to grow, and with that came new uses for copper, most notably in the transmission of electricity. So the transmission of electricity by copper meant that quality was now becoming increasingly important. So these two challenges, the reduction in head grades and the increase in the importance of quality, gave rise to 2 quite important innovations in copper. The first being electro-refining and electrowinning. So this was pioneered in the Pembrey Copper Works in Wales in 1869, and this enabled the production of much more pure copper than what was possible before. Simply put, electrowinning it takes dissolved copper ions from solution and deposits them onto a very pure cathode. You can produce 6 nines copper using this process. And to this day, electrowinning and electro-refining is the go-to method for producing high purity copper. So the next stop in our journey takes us to Broken Hill in New South Wales. So as I mentioned, by the late 1800s, the high-grade ore deposits were rapidly diminishing, and the ore available for direct smelting was almost all gone. So the need for pre-concentration was becoming increasingly obvious. But how? Well, along came flotation to save the day. Flotation was born in the tailings dumps at Broken Hill Proprietary, or BHP as they're known today, and Zinc Corporation. That was the industrial birthplace of flotation. And this was a massive innovation for Australia in particular, and what it meant is you could unlock deposits of copper that were previously not viable. You could go through your tailings, recover copper that was not able to be recovered before. And it wasn't long before this was standard practice for copper. I mentioned it was developed in lead and zinc, but within less than 10 years it was used in copper pretty widely. So our next stop takes us to Finland. And post-World War II, Finland were really struggling with much higher energy costs than they had before. They lost about 26% of all energy production to Russia, and the availability of fossil fuels was inconsistent at best. This was a really tough time to be a Finnish copper smelter, and the team at Outokumpu's Harjavalta smelter rose to the challenge and developed a method to use the internal sulphur and ferric content of the ore to provide the energy required for smelting. So this was the birth of what's now known as the Metso flash smelter. And the two gentlemen that developed this technology were able to find that method and produce 96% of the energy required to get the temperature to what's needed for copper smelting. So because of this, it was much more energy efficient than roasting or whole of ore smelting, and it became very widely adopted as a highly efficient method for producing both copper and nickel concentrates in particular. And to this day is still the most widely used efficient method for doing this. So by 1968, flash smelting had been widely adopted, and the production of sulfuric acid as a byproduct of the sulphur was standard practice. So what happened back then was this sulfuric acid was sold as a byproduct. The thing about sulfuric acid is it's great for leaching copper. You just need to be able to upgrade that solution to be able to recover it efficiently. And this is where solvent extraction came along and transformed the hydrometallurgical production of copper. So solvent extraction wasn't new at that time. It had been used in many other applications since the 1800s, but it was at Ranch's Bluebird mine in Arizona where it first found its way into copper production. And this was a real game changer because compared to the previous cementation project, it was much more efficient and much more effective at producing a solution that could then be used in electrowinning to produce very high purity copper. And since the 1970s, this process has become very widely used in the copper industry and is responsible for about 25% of modern copper production. So these days, at Metso, we didn't invent solvent extraction, but we have had about a 45-year history in providing solvent extraction solutions for the mining industry. And in this picture is one of our VSF, or vertical smooth flow reactors. They're very well known for being highly efficient and very safe to use as they're a fully sealed and modular unit. So since the 1970s, there's been quite a number of innovations that have been both copper specific, but more broadly specific to mineral processing plants to enable more efficient metal production. The Ausmelt TSL process, which is similar to the Isosmelt process, is based on top submerged lance technology, and you can handle a variety of different concentrates with this sort of technology. Lower concentrate grades, polymetallic ores, for instance. Also, over this time, the tendency has been to grind finer to liberate more of the valuable mineral. And what this has meant is that there has been a generation of fine material that might be lost to tails if not able to be recovered. And this has given rise to technologies like Glencore Tech's Jameson cell and the more recent Metso Concord cell. These are able to capture particles that would otherwise be lost to tails more efficiently than using conventional flotation methods. One other innovation that's happened that's relevant to copper would be the use of HPGRs in mineral process plants. HPGRs, if you use them in place of a SAG and ball mill circuit, can provide significant energy savings. It's probably fair to say that the adoption of this has perhaps been slower than anticipated though. Other technologies like the use of X-rays for measuring copper concentration around a flotation circuit and coupling that with things like a camera over the float cell that would, and an advanced process control system means that an operator is more efficiently able to operate their circuit, maximising recovery, reducing waste. More broadly, process control in general has had a big impact on plant efficiency, and things like remote condition monitoring mean that plant operators these days can more or improve their availability and the reliability of their process, producing more with the time that they've got. A couple of more novel technologies that have come about recently would be coarse particle flotation. So this enables someone to upgrade an ore very early on in the flow sheet and not grind as fine, which means not wasting as much energy to recover the same mineral, like copper, for example, or the copper minerals, for example. Bioleaching has become popular, probably more so in gold, but now we're finding applications in bioleaching. So that's the use of bacteria to break down the sulfur content of the ore to liberate copper. So coming back to our challenge, what do we need to do? Well, definitely we need to keep going with the exploration activities and find more greenfields and expand our brownfields. But we also need to make the process, both new and existing, more efficient. We need to be able to improve recovery, reduce energy consumption, improve reliability and availability, and increase throughput. And we also need to find new ways of unlocking deposits of copper or sources of copper that might not have been able to be processed before. This would include urban waste, or urban mining, or recycling. So a quick look at what we need in terms of CapEx investment. So the UBS is suggesting we need about $150 billion invested in copper CapEx by 2035. And you can see that BHP and Rio Tinto are key players in this with things like Escondida, the Josemaria project, Resolution. But even with all of this, we're probably still going to fall short, is the current forecast. So we can use less, we can substitute, and we can thrift up to a point. It was mentioned in one of this morning's presentation that substitution and thrifting is not straightforward. We can definitely reduce waste in process plants and reduce OPEX. And we can do this by embracing new technologies. HPGR uptake's been a little bit limited. This is a genuine opportunity to reduce the amount of energy in flow sheets if it's embraced more readily. Fine particle flotation could be another way to reduce waste, as I mentioned, as well as more rapid uptake of things like advanced process control, online slurry analysis, and the use of things like froth cameras, ideally considering these during the development of the Greenfields project, not retrofitting them to that project a few years later, getting in early to capture that or maximise the opportunity. Recycling and urban mining is another area of criticality, and it's important that we use an efficient technology and versatile technology with low emissions for processing this waste. And pictured here is one example with the Metso Caldo process. One big task for OEMs like us is to continue to invest in R&D. We've got over 7,900 patents. We have played our role, but we need to continue to play that role and invest in R&D. Okay, so we're definitely facing some new challenges with copper, but also some not so new ones. There are some projects in the pipeline, but it's unlikely we're going to overcome that gap, or that forecast gap, at the pace required with just scaling alone. We need to make the existing operations more reliable than the past and more efficient. We need to continue to develop new technologies and embrace them readily, and the good thing is the copper industry has had a very strong history of doing so. So at Metso, we're not investors, we're not explorers, we're not miners, we're not plant owners, but we have a very important role to play in enabling all these players by bringing new technologies to the market and making existing plants more efficient to be able to do more with less. Thank you very much.